like what are those? It comes up like for database indexes we are using the B plus trees, but not many people are clear about like how they actually get used, or like what are the various B plus trees, or how the actually indexes are getting created, or why they even needed. So in this video, I'll explain in a systematic way, like how the data is getting stored on the disk. Like before we understand why there is a need for the indexing, how the indexing happens, I would actually tell you like how the data is actually getting stored on the disk, and why there is a need of indexing, and what is indexing, and then we'll go into the multi-level B tree, and then the eventually B plus tree, and how it is actually getting used in the creating the indexes, and why it is so popular, and why all the databases are using it. So let's actually get started with the what is a disk, maybe, right? Like, or how is the data stored or arranged on the disk? So simply what happens here is, like as you might aware, like eventually, no matter what the program, let's say this is RAM, any program that is there, what it does is it kind of let's say this is my prog- program. This kind of whenever it has to do anything, it actually like fetches the data from the program, or like from the disk, pass it to RAM, do kind of like whatever the operation that it has to do, and eventually it will kind of persist it into the disk. So the persistence would happen here, right? RAM, or like memory, call it, right? So that's how most of the programs works. I mean, in the CPU world, similarly for the GPU and all of those things. But again, the concept of memory is still there, and eventually the persistence, the data is getting stored in the disk eventually, right? We'll talk about more about it, but in the very simplistic sum, that's what it is. But if you look at on the disk, how the disk is actually structured. So disk is nothing but, let's say, sorry, let me just choose a, yeah, here, disk is nothing but, let's say, there is a this spindle that is there, right? This rotating disk that is there, this head would kind of go into various places, it will be keep on spinning, right? And we'll read the various data from the disk. How it happens here is basically the disk are nothing but like in the form of the sectors that are there, right? Like all these round circles that you are seeing, these are nothing but the tracks that are there. Sorry, yeah. And then these lines that you are seeing, these are nothing but the sectors that are created. So as you can see, like now we have divided this work, like all of this, these circles, concentric circles, have been divided into the smaller blocks, smaller parts, and those parts are called nothing but the blocks. And there, those blocks are kind of nothing but, you can identify them using like the track number, right? Track and sector. So this is how what the blocks are, and these blocks are basically stores data. Like whenever the data is getting stored, it's getting stored into the blocks, right? But this is the typical the order that is there. And let's say, I mean, block size is 512 bytes. Like each block is a can store 512 bytes, right? So this is your address, and that's how like the data gets stored. And whenever the read and all of those things happens, as you can see, like why I'm bringing the track and sector, this gives you a address of a particular block. This size of the block could be higher, depends on the manufacturer how they are doing it, but for simplicity, let's just take is the 512 bytes, right? So this is how the disk is. uh, let's go further in the database concept, or let me just say how table data is getting stored and like written or read from disk, right? So let's say this is a table that I have created. That table is name is DB table, or any name that you would want. It has like few fields: ID, name, title, timestamp. Let's say, for example, for the ID, it is a 10 bytes that it is taking, and if overall for all of these, probably like this is for 30 bytes. This is maybe like again 30 bytes, thir- or yeah, 40 bytes, right? At 80, and this is maybe, let's say, 48 bytes for the simplicity, right? This is my size. These are anyway defined in the table how it is taken, and so basically for every entry it becomes 128 byte for each row. For example, here, let's say, in this table that is there, I have 100 entries, right? uh, ID is there, and then all of these columns are kind of populated. I'm not populating it here. What will happen here is, let's say, the ID one, the entry one that would come up, as I have written here, like 128 bytes are there. So that would mean like the block size I have already taken as 512 bytes. So entries per block would be 512 divided by 128, which will be four entries. What that means is, here basically, let's say, this is your block. Here, let's say this starts with this is the 0th byte, and probably somewhere here it will be the what do you say, last byte, 11 bytes, right? And how it can be stored is basically like these. Let's say the first byte starts here, like from the starting. The second byte is starting from here, like the second entry is starting from here, not the byte, right? Third entry is starting from here, and then the fourth entry is just starting from here, right? So these are like few points, right, which will be, let's say, probably this would be 127, or like 128. This would be probably like 256, something of that sort, right? So these are called nothing but the offsets. Okay. Now what's happening is, here is, let's say this, uh, again, let's say there is a few more entries. Let me just add 3, 4, 5, right? 6. So 7. All of those. So let's say what will happen here is, let's say the first four, and like these four entries, they are going into, let's say, this sector, or like this block, right? Next four would go into like probably a dislot, right? For these 100 entries, then we'll require maybe like how many every block is having four entries. So these 100 entries would be stored in like 25 blocks. So that's how we have written it. As the entries are coming in, we are kind of going into the slot, going into the particular block, and whatever the data that is available, like last offset that is available, we are appending to it. And it could be, I mean, here this might give you a sense of uh, random writes, but it's more of a sequential writes. I mean, we can go into those sectors and whatnot. But when I kind of do the read, right, there could be the queries, something like similar to select star from DB table where ID is equal to 92. Right. What this means here is, like, basically I don't know where the data is stored, so I'll have to actually go and scan all the 25 blocks. So I'll read the blocks one by one, as I have kind of told earlier, like where the RAM, this program which is doing the query processor, it will kind of go read the block, load it into memory, and then kind of figure out what is the, if the id is matching the id is specified in the where clause. So in the worst case, you can see like with this approach, I'll have to do like 25 block scanning, scan 25 blocks, right? As you can imagine, like if this is maybe, let's say, the 1,000 entries, then it will be like, it will be in some of the cases it can, in the worst case, it will have to scan like 250 blocks, and the 1,000 is a very small size, right? So what we could do is basically like build a index on top of it. What that means is basically like, if I know, in this very simple terms, if I know like where is my entry one is stored, like what is the uh, track sector and offset. In that case, I can do just that particular lookup, right? I mean, I can go to that place and actually read that particular block. So let's just do that. How we can do that is basically, let me just copy this, or I have copied a few things here. Let me, yeah. So what I could do here is maybe, right, I can kind of create, let's say, the here this will be my ID, and then I'll have the record pointer, right? I mean, in this entry, it will be, let's say, the record pointer is nothing but the track sector and then the offset, right? That gives me the location of the block where it is. Let's say the one would be there, then the two would be there, right? All of these IDs I can actually define where the blocks are stored. So these would be kind of having the pointers. Let's say the pointer, like this particular data where it is stored, like pointer for these entries. Eventually, is the location of this one. Right? Similarly, for two, it will be this. So for every block, now I know where the in which sector, which track, which sector, and at what offset the data is stored. Right. So for simplifying, like let's say there are 100 entry. For ID, as we have like that, this is taking 10 bytes. And for example, like this record pointer is maybe like taking 6 bytes, right? So for per entry size would be 16 bytes, right? And then again, like where this data would be stored, this will again be stored in these particular disk only. But as we know, like okay, how many index entries per block I can add, that would be 512 by 16. So it will be 32, right? Yeah, so like 32 entries per block. So that's what I can show. Now if I can kind of go here, you can say like I have 100 entries, so how many blocks do I require? 100 divided by 32, which will come around 3 plus something, 3 point something, right? Let's just consider 4 blocks, right? So now, for example, here, like these 32 entries would be kind of stored in, let's say, some block, right here. And when I kind of do the scan 25 blocks, this was the case without the index. Without the index. Now, if I have to again the same query, it will take how many? Let's say first thing is when the ID came in, I'll kind of go here, try to figure out like in which block my ID is there, right? So here, like I'll read the one block, two block. At in the max worst case, I'll read the 4 blocks. Out of those four blocks, I can find the record pointer for the actual data. So this will be 4 plus 1, which will be read 5 blocks to get this query, right? I can actually, this is the case, and then probably here, let's say if this becomes 1000 entries, I could kind of add one more level. Can I add index for this? Let's say this becomes your 1000 entries, all right? Here, let's say the 1000 entries are here. That would mean like how many? Here, I'll just increase 1000 by 32. It will be around, let's say, the 32 block or something, right? Uh, yeah, 30 or yeah, whatever. uh, 30 plus blocks. That again becomes quite high. So I could do one more thing, which is basically add a similar further index here. Maybe that will have lesser thing. Again, like these are dense indexes, so then I can have probably lesser indexes here. Like if it is just the ID, that is what I'm having. Like for these IDs, whatever all the IDs that are there, I can have it here. So this is what the multi-level indexing would look like, right? So this basically it will kind of do that, and my uh, blocks that I need to scan would reduce, right? And this is basically, if you can see it, this is nothing but the indexing. Why indexing is required? If the 1000 entries are here, you are doing the 1000 block, or let's say 400 blocks scan. But if you kind of change it here, in the 1000 entry case, it will be mostly like 50, right? uh, 50 entries, right? I mean the 50 blocks that you are doing, which had changed from 250 to 50, or yeah, 50, 40, whatever those blocks, 32 or something. And then I can reduce it further. That would be like lesser number of blocks, and I can kind of do it in within like few blocks, only few block scans, or even like bring it into a couple, or like one block or couple of blocks only, right? So this is what the indexing. Now, as you can see, uh, this is where like the first level of index, we call it as dense index because everything is there, dense index. And this becomes more of a sparse index because this index over index. And similarly, I can keep on adding the index, but this is becoming more of a chain. In simpler terms, let's say the dense index is here, right? Probably like the this data is here, right? This is the data here, and then I can have even smaller index. So this becomes my multi-level index, right? Something like this, right? Which will have one entry would be like probably here, for these many entries, right? This is pointing to all those other entries. Similarly here, as you can see, like this is more for like these many entries, like these are increasing, right? Every entry is kind of pointing to various data points, right? And eventually like this would be kind of pointing to right, whatever the dense index, sparse index. So this is how the multi-level indexing looks like, multi-way indexing. This is how, like, but if I kind of change it slightly differently, right? If I just uh, turn it around, like as you can see, as I'm creating the indexes and over indexes, it's nothing but becoming more of a tree, right? As you can see here, right? It's some way of tree, right? Here, uh, and these would be kind of pointing here. So this is how, like, why like, I mean, these indexes get created. And I hope you are able to understand like why the indexes are required, because if you do the sequential search and like sequentially go through it, your read times would be much uh, slower. And as all of you have read, like let's go back, as there are multiple levels that are getting created. How quickly can you go to the particular level, right? So the initial concept that we had was like the basic concept is the binary search tree. How quickly can you search these, and that has like few other things, which is the data is sorted and all of those things, like the keys are sorted and all of those things. And then we can always find out, let's say if this is 20, 10, 5, 15, right? I can always search through maybe like 30, like 25, 40. Right, so I can do this. Like, I mean, what happens here is nothing but you just see the search, and then basically, like, at the law, whatever the number of levels that are there, you can eventually go and figure out where your data lies. But this is a BST tree, like binary search tree, which is fine, like for a simplistic use cases. But as you can see, like the number of keys and all of those things could be much higher. So there is a concept of MV trees also, right? The way you have the BST, the binary search tree or a binary tree, right? Which has like two children. Similarly, in the MV tree, you can have like your M children, right? And then you can have like let's say the M minus one keys. Here you can kind of define it, all of these keys that are there. Let's say 10, 20, 30, right? So you can kind of define all of those things. Probably anything that is smaller than this would fall left, right? I mean, this will have a few other things. Another thing that can happen in the, like, that we typically have in the MV trees is along with the keys, like let's say these whatever the node definition for a MV tree is nothing but the list of or let's define the what do they say, the I mean, it will have the list of keys, and then list of record pointers, right? We can merge these, but in the simpler term, what this will have is, like in the node, there is a, let's say the key is there 10, there is a record pointer. Similarly, for every key, there'll be a there could be a record pointer, right? Similarly, for every key, like 30 would also have somewhere record pointer, like for every key, whatever the data that is there. So here, as we kind of looking here, it will have all of those things. We can fill up this MV trees, right? The thing is, like, I mean, whatever the, let's say if you are having the keys as 10, 20, 40, 50, something like this, right? You can kind of keep on adding those here in whichever way you would want. But the one major problem with the MV trees is you can kind of define it in any way. Like the trees have can have M children and M children and M minus one keys for MV tree. But there is no restriction, like how do you want to kind of configure it. So it, in the worst case scenario, depends on like how you are kind of configuring it. You can actually make it a chain, like for the problem typically we might have in the unbalanced trees, right? So the here the depth would become maybe let's say the m, or and like whatever the number of keys that are there, I can kind of keep it in the chain, in a chain way. So this is where, like, the even if the MV tree has a concept of having like multiple keys, multiple childrens, and all of those things, because in the two keys it will be, the tree would be slightly the height of the tree would be much higher, and to do the lookup even in the BST, if we, even if it takes like log n, but the uh, lookups would be much higher, and our request would not be that fast. MV trees are there, which takes care of like adding multiple keys in a particular node and having multiple children, it reduces the height. But the problem here is because everything depends on the constructor, like how it is getting constructed and all of those things. And the worst case is the complexity could be order of n, like all of these blocks that are there. So that's where the B tree comes into the play. B trees are nothing but the MV trees only, but it has few extra rules, and those rules are nothing but basically it helps. Right. These are nothing but like every node must have at least my2 childrens before creating a new node. Root node should have minimum two children. Like if the cardinality is let's say 10, every node should have at least five children before we create a new node. Root, because it can't have five nodes, because I think that the tree would not be formed. So at least minimum two children should be there for the root. All the leaf nodes should be at the same level. What this does is basically it avoids these chaining kind of situations, and the tree would be balanced. And the second thing is basically the creation process is bottom up. What this let's just kind of try it out. So let's say I take a B3 B3 with right the children 3, or right the children equal to 3. So yeah, let's say these are my numbers 100, 200, 400. As I can kind of keep let's say the three keys. I mean it will be can have yeah, I mean the keys I'm going ahead with the, let's say keys I'm keeping the keys to 3, or the cardinality to 4, like how many children could be there. So let's say the 10, 100, 200, 400 came here. But once the 500 came into the play, what will happen here is we'll kind of divide this into two nodes, right? So this will have maybe like this will go here, 400, 500 would come up here, and this will have right like this. And then let's say so let's say we kind of have 500 and 600 came, 700, 800, right? So let's say 500, 600 would go here, 700 would go here. Then the 800 came in. 800 ideally should come here, but there is no space. So what will happen here is we'll divide this node. So let me add one more node here, right? It will be kind of the node came here. It will have 800, and then we kind of what we'll do is we'll add the 700 here. We'll remove the 700 from here, and then kind of make this change, right? And then let's say the 300 came in. 300 came in. It will go here, right? Now let's say the 350 comes in. It should go here because it's less than this 400. So what will happen here is we'll kind of divide this block here, right? So it should become like 100, 200, 300 we'll move. So let's say the 200 and 400 would, or sorry, the 350 would come here. We'll remove these 100, 200 we have moved there. Here we'll add 300. So this becomes your 300, 400. So this is a four-way tree, and then has right. So this is how it will become. Now I can kind of keep on adding more and more things. Like if there is a 150 or something that come in here, more nodes would get added. Let's say the here probably here let's say the 50 came up, 50, and then 100 is already there. Then the 15 came in. So I can kind of divide these things, and then there'll be new nodes that I'll kind of add, keep on adding. So this, I mean, you got the idea how the B tree would be helping us implement the multi-way search. Let me just do that. Basically, what will happen here is I'll kind of uh, divide here. There'll be two nodes, so this will have 50, like 150. Sorry, let me just 150, 50, 150. Right. That will have like my 50, 100 would come here, and then I'll kind of have 150 and 300 would shift here. I'll kind of would not have here, and this basically this node I'll move to up, okay, slightly. But let's say the node would come up here, 400, and this will have like this is how it will split up, 300. It will be again, let's say the 350 would go here. There'll be this, and I'll add one more node here in between. Call it, let's say the 200 would come up here. 200 would come up here. 700 would be like uh, this side, right? Whatever it is, just to kind of give you that chance, like it's smaller than this one. So something like this, 600, and then 800 would be there. I hope like I have covered just one more error here. So this is what will come up. Okay, and then all of these would have record pointers. So from here there'll be record pointer for all the keys, right? There'll be record pointers, because that's what we have talked about, like whatever the in the multi-way search when we were talking about like all these record pointers. So B tree is nothing but this one, right? Here you can see that like it's a way of implementing the multi-way search. You can do those queries like depending on the query or the keys what you are looking for. The B plus tree is again similar. The only thing that it does is basically so B tree and B plus trees are similar, but only difference that is there between the B tree and B plus trees is like the record point. The okay, I kind of missed this 400. Let me just fetch it. Okay, so this is my B tree, B plus tree, but the only thing is that now the way we were having the data here in the B trees, we are not storing it with every key, rather than the pointers to the actual data resides in the leaf node only, and all the other B tree rules are applicable. The other thing that it does is all the leaf nodes are connected, right? So what will happen here is, let's say the in the B tree, what it will start doing is basically it will have the 150 also here, right? That's that. So the keys would be repeated. Let's say this 400 would come in here, right? Uh, so 400 key would be repeated. This will have 200, and let's say the yeah we are kind of right biased or left biased, that you can define. So here I'll put the 300 right here in this particular keys. 150 would come up, and then similarly here I'll kind of put the 400 also. The keys are kind of getting repeated. That's all that is happening, right? Similarly 700 would come up somewhere here, right? And these are nothing but your this becomes your B tree, right? So these are connected, and then what's happening here is like the pointers to the data, like record pointers, are basically with these keys, like at the leaf level, and all the leaf levels are at the same level. It kind of makes sure that your height is balanced, right? But if you kind of go back, right, your queries could be much faster. You will figure out whether your key, like in which side of the key your query key is falling, based on which you can do the lookup, and within like a couple of hops you can find out what is your record pointer. And it also depends on how many children you want to have, like how many keys you want to have in each and every node. So this is what the B plus trees are, and how they are kind of getting used in the indexes. It's not only limited to the SQL databases, but even in the NoSQL, like a lot of the ideas are there, how B plus trees are getting utilized. I hope this gives you some idea about how to kind of, I mean, how the B plus tree or the indexing work from disk and all of those things, and how the B plus trees would help you understand, like query B plus tree. B plus tree data structure helps you arrange the data in a way that